Good morning, students. After a long break, today we are going to see about hysteresis. So, when a magnetic material is kept in the magnetic field, it gets magnetized. So, the magnetizing field is represented by H, and the magnetization or the magnetic induction is represented by B. So when a magnetic material is kept in a magnetic field, it gets magnetized. So as the strength of magnetic field increases, the magnetic property induced in that material will also increase. So the magnetization depends upon the magnetizing field. When a ferromagnetic material is magnetized in a magnetic field, we observe that magnetic induction induced in that magnetic material lags behind the magnetizing field. This lagging of magnetic induction with respect to the magnetizing field is called as hysteresis. In Tamil it is called as Gantha Tayakam. So let us plot a graph. So when a graph is plotted by taking magnetizing field along the x-axis and magnetic induction along the y-axis. So when the magnetizing field is 0, magnetic induction is also 0. As I increase the magnetizing field, magnetic induction also increases and reaches its maximum value. So beyond this, if I increase the magnetizing field, magnetic induction will not increase. So this is saturated magnetic property. So magnetic induction becomes a saturated value. So this is not a straight line. So if I take slope, the slope will not remain constant. So when the magnetic induction reaches the saturated value, now let us mark this by AC. Now when the magnetizing field is decreased, magnetic induction will also decrease, but it will not along CA. Instead of that, it will follow a different path CD. So when the magnetizing field becomes 0, still the magnetic material retains some magnetic property. This magnetizing property retained in the magnetic material is called as retentivity. So here AT represents retentivity. So to bring this magnetic induction to 0, now I have to magnetize that magnetic material in the opposite direction. So I have to give negative magnetizing field. When negative magnetizing field is given to that magnetic material, then the magnetic induction in that material decreases and becomes 0 for a particular negative magnetizing field. So this is represented by AE. This AE is the negative magnetizing field which brings the magnetic induction to 0, and this AE is called as coercivity. So coercivity of a magnetic material is the negative or the negative magnitude of the magnetizing field that brings that magnetic induction to 0. Now, if the negative magnetizing field increases, then what will happen? The magnetic induction will increase in the opposite direction and it becomes saturated value at a particular magnetizing field. Beyond that saturated value, magnetic induction will not increase and remains constant. Now, if I decrease the magnetizing field, then the magnetic induction will also decrease, but it will follow a different path and reaches this point. So let us call this as G. Now, this AG measures the magnetic induction retained in the magnetic material when magnetizing field becomes 0. So this is negative retentivity. So to bring this negative retentivity to 0, again I have to apply magnetizing field positively. As I apply the magnetizing field positively, then what will happen? For a particular value of the magnetizing field, magnetic induction becomes 0. Here AK again measures the coercivity, positive coercivity of that magnetic material. Again, if I increase the magnetizing field, again it will reach the saturated value. So now, this magnetic material is taken through a cycle of magnetization. So when a magnetic material is taken through a cycle of magnetization, you will get a closed curve A, C, D, E, F, G, K. This closed curve obtained when a magnetic material is taken through a cycle of magnetization is called as hysteresis loop. So what is the use of the study of hysteresis loop? So when a magnetic material is taken through a cycle of magnetization, all the magnetizing energy given to the magnetic material is not utilized to magnetize the magnetic material. Some amount of magnetic energy is lost, and this loss is called as hysteresis loss, and this hysteresis loss is dissipated in that magnetic material in the form of heat energy. Actually, this loss of the energy is utilized to turn or to rotate the molecular magnets that are induced when that magnetic material is taken through a cycle of magnetization. And it is interesting to see that the loss of magnetic energy is proportional to the area enclosed by this hysteresis loop. So when we study the hysteresis loop of several magnetic material, especially ferromagnetic material, we can get a knowledge about the loss of magnetic energy when that magnetic material is taken through a cycle of magnetization. From the knowledge of the loss of hysteresis loss, we can select suitable magnetic material for suitable purpose. For example, let us consider two ferromagnetic material, that is soft iron and hard iron. Soft iron is, so ions are classified into hard iron, soft iron, weak iron, soft iron, like that we have steel, depending upon the carbon content in that iron. So when we take soft iron and hard iron, soft iron is called steel iron and hard iron is called as carbon iron. So when the soft iron and the hard iron are taken through a cycle of magnetization, and if we draw hysteresis loop, we can observe that for suppose, let us take it as soft iron. If this is for soft iron, then for hard iron, you will get a hysteresis curve whose area will be very large. For example, this is the hysteresis curve for hard iron. So this is soft iron and hard iron. So when you see the hysteresis loop of a hard iron, it will enclose a larger area. So from the study we can see that when soft iron is taken through a cycle of magnetization, only little amount of magnetic energy is wasted because the area enclosed for the soft iron is lesser. On the other hand, if a hard iron or carbon iron is taken through a cycle of magnetization, it will have a hysteresis loop which will enclose a larger area, which tells that large amount of energy gets wasted when hard iron is taken through a cycle of magnetization. So, when you see the retentivity and the coercivity, it is smaller for soft iron, but it is larger for the hard iron. So we can comparatively compare the soft iron and hard iron by studying hysteresis. So what are the properties of hard iron? One, when the hard iron gets magnetized, when magnetizing field is removed, the magnetic property existed. So magnetic property persists in the case of hard iron. In the case of soft iron, it disappears. Secondly, retentivity and coercivity is large in the case of hard iron and it is low in the case of soft iron. Third one, susceptibility and permeability. Susceptibility and permeability are low in the case of hard iron and it is larger in the case of soft iron. Larger in the case of soft iron. Hysteresis area is larger. So energy lost is also large and area is small. So magnetizing energy lost is also small. Hard, since it is having persistence, this retains the property of magnetism. It is hard iron is used in the case of core of the transformer, solenoid in this case. But soft iron, since loss is very small, it is used as the core of the transformer. So it is used for permanent magnet. Example for hard iron, carbon iron, steel, then lodestone are the example for hard iron. Very soft iron, for example, for soft iron, mu metal. Mu metal is an alloy of nickel and aluminum. Mu metals, alloy are example for the soft iron. So, by the study of hysteresis loop, we can select suitable magnetic material for different purpose. So this is how the study of hysteresis curve help us to draw hysteresis loop, and from the hysteresis loop we can classify different materials as different categories. From that we can select suitable materials for magnetic materials for suitable purpose.